Yeah, can you hear us now, Josh?
There's sound now.
You should get very close to me because yes, no, very close actually.
I don't want to be that close. They don't hear my info. That's fine.
Yeah.
Welcome to the first CS World Team of the Year. It's our pleasure to have Alessandro Roncone.
Yeah.
Presenting his work today. Alessandro received his bachelor's of science degree in biomedical engineering from the University of Genoa, followed by a master's degree in neuroengineering, also from Genoa, followed by a PhD in
Robotics.
robotics, from the Italian Institute of Technology, which I first read as IIT. And I was surprised that he'd gone there, but it's the Italian IIT, also in Genoa. Following his PhD, he went on to Yale for a 3-year postdoc in the social robotics lab before joining CU at us in 2018, where he's an assistant professor. He's also the co-director of the College of Engineering's IRT on engineering education and AI augmented learning. And that's sort of related to his work with the AI Institute on student AI teaming. So today he's going to give us a rundown on the work going on in his lab.
Thank you. Thank you, Jim, for the introduction. Can you hear me over Zoom? Can you see the screen? Everything works? Fantastic, you confirm? Okay, cool. So thank you all for being here. I'm very glad to see so many people face to face. Joke of the day, I know that half of these people are here because outside is very hot. But I hope this is going to be a good, interesting 45 minutes to an hour presentation. So today I'm going to be giving you an overview of the research that my students and I have been doing in my research group, which is called the Human Interaction and Robotics Group. If you want to know more, please visit this link. And for those of you who don't know me, my work is within the broader area of human-robot interaction. So give me a sec. Human-robot interaction. Yes. Okay. Which, broadly speaking, deals with the problem of integrating robots in human-populated environments. And the reason for which one may want to do that is that robots can be very useful to people. They can provide assistance, support. They can replace human in dangerous, tiresome tasks. They can augment humans. And this concerns both their physical capabilities and their cognitive capabilities. And all this is, in my opinion, extremely interesting. But what is more interesting, in my opinion, is the fact that all of this development is happening in parallel with broader shifts in the field of robotics. Because I think it's important to remember that historically robots have been developed to replace people in a variety of different applications. This is the most successful application of robots to society, big industrial robots that are in factories that work 24/7, 364 days a year. They move very fast, they're very dangerous, and they never break. But in the past 20 years or so, we started to hit a wall in terms of pursuing this paradigm of full automation. And there are plenty of examples of big forward-looking companies that are reintroducing humans back to the factory. And I don't want to spend too much energy and too much time talking about this specific problem, but I think this is a good example of the fact that autonomy and automation still have a long way to get to the level of human performance. Humans are still much better than robots in a variety of different tasks. This includes tasks that involve fine manipulation, tasks that involve cognitive complexity, things like wiring things into a car, the stuff that is very hard for robots. Anything that involves precise perception is another thing that is very difficult to do with a robot. So for this reason, we have more recently shifted toward the paradigm in which people are helping robots achieve tasks in a more complex environment. So robots are basically doing the same thing they were doing 20 years ago. But now we have humans with their superior perceptual, cognitive, motor capabilities that are augmenting robots in a variety of different applications. And this is better for humans, this is better for robots. There's a lot of interesting research in this space. Robots need to still interact with people. But I think that it's also interesting to see this as a transition. So we were operating in a paradigm of robots replacing people. Now we are operating in a paradigm of people helping robots. This is the present and the near future of robotics. What everybody is working towards is a far future in which robots are effectively augmenting and supporting humans in a variety of different applications. And this, again, is a very broad umbrella of applications in which robots can be useful, from logistics, manufacturing, construction, healthcare, and finally service and home robotics. And they're going to be dealing with people in a variety of different domains, deal with untrained people, predict human behavior, and interact naturally with them. But I think that, again, all of this is extremely exciting for us that work in human interaction, but there are two sides of this. One side of it is the fact that this, in my opinion, is a broader societal, economical, technological need that we see the field being pulled towards. But on the other hand, there's also an opportunity in terms of pushing the state of the art in the field to make this vision of robots helping people materialize. And this is a good summary of the research that we do in our lab. On one hand, we have this strong motivation, these interesting objectives to work toward. On the other hand, we sit on the state of the art of robotics, and robotics and robotics at large. This includes also neighboring fields, AI, machine learning, and so on and so forth. We sit on the top of the state of the art of human-robot interaction, which generally deals with translating these the problem of human-aware and human-in-the-loop systems. And we work to move the state of the art toward this broader vision. I believe we are going to get there by looking at robotics as a system science, and in particular by investigating three core fundamental problems in this space. And these three problems are also constituting the three research strands in our group. I'm going to be talking about this for the duration of this presentation, so this is also serving as an outline of today's talk. But briefly speaking, these three groups are the group that works in physical HRI, so robots that are safe to people. The second strand is working in the robots that are performing in complex environments. And lastly, robots that are better teammates. So before we delve deeper into the research we've been doing in these three areas, I would like to just highlight the fact that I will be here without the help of the great students that are working in my lab. So first of all, shout out to you guys. You're scattered around in this room, but you know who you are and the faces are there. And second of all, if you're interested in any of this of the work that we are going to be showing today, please visit this link, send them an email. They are more than happy to have a chat and talk about the interesting research. Lastly, for reasons of time, I'm not going to be covering all of the things we are doing in our group, but I hope that this is going to be a good overview. Okay. So before I move into the specifics of the research we are doing in these trends, I would like to introduce now a motivating example that I will be using throughout this presentation. And this example is the problem of collaboration in close proximity. This is just generally an interaction or a metaphor in which an agent, multiple agents are sharing large portions of the operational space, and they are operating in close proximity both in space and time. And again, you can choose and pick your application. These are just some examples. But in general, I find this particularly interesting for two reasons. One, these are good prime domains in which I would like to see a robot operate in and help people. You can go, again, you can choose every one of them. But the other aspect of this is that these are particularly challenging for robotics. State-of-the-art robots, state-of-the-art robot controllers, state-of-the-art perception and motion planning systems cannot perform in these constrained environments. And not only that, but humans are also particularly good at operating in these constrained environments. So if I were a business person, I would never invest money in people that are trying to develop robots for these applications. Because we are not there right now, right? But I'm not a business person, I'm a scientist. And this is extremely challenging and extremely interesting. So one research question that one can ask is how can we move the state of the art to allow these robots to efficiently operate in close proximity with people? And again, this problem means different things for the 3 different strands that that we have in our lab. So let's start with the first one, which is the strand that works in physical human-robot interaction. This is the problem of robots interacting physically with people, robots being safe around the people, robots avoiding people, and so on and so forth. This problem of collaborating in close proximity is challenging for the physical human-robot interaction group for a number of different reasons. So if you look at my favorite example, which is the professional kitchen scenario, I don't know if you've ever worked in a professional kitchen. I did. I wasn't cooking. I was a waiter. But the first thing that I remember is that it is a very high pressure environment. There is a lot of cognitive and physical load on the agents that operate in this environment. The second component is that there are significant safety concerns, burn hazards, sharp objects, other people, and so on and so forth. There are multiple agents with potentially competing priorities, and there are a lot of constraints, so high clutter of objects, there's a lot of mess, and most importantly, you are going to bump into each other. So collisions are something that you need to account for in your control and motion planning. Okay, and all of this is a problem for robotics. All of this is the subfield of research in robotics. But for the purposes of strand 1, we look at this as a perceptual problem first. Robots, state-of-the-art system right now cannot perceive obstacles and humans in this messy environment with the precision and speed that is needed to operate in these scenarios. And so if you just make a simple example, you have a robot. The robot is surrounded by a lot of obstacles and the clutter, and the traditional systems would place a camera that is externally mounted, could be a depth sensor or whatever it is that you're using to do vision-based perception of the robot and its environment. But because of all these constraints, some objects might be detectable, some objects might be not. And this already starts to be a problem. You might be adding multiple cameras. You can have a camera over here that perceives this object from this side. But the problem is that if you increase the complexity and the clutter in the space, this doesn't scale up. And to solve this problem, one may look at, again, what the humans do in these complex scenarios. And one important difference is that they sense the environment from their own egocentric perspective. And this means that they look at the scene from, with vision from their own body, but they also integrate this information with the sense of touch, which is extremely important when operating close to each other. So again, this is a strong motivation for us to pursue research in developing artificial tactile sensing for robots. This is a big field of research. And this has the advantage of not suffering from occlusions, and most importantly, of providing complementary information to vision. So we can use this different type of information to enrich the amount of data we get from the environment and better behave in this space. Another thing that humans do very well is not only perceiving from their own perspective, so onboard sensing, but it's also perceiving particularly well in a region of, in an area that is in the area that is immediately surrounding their bodies. This is the concept of peripersonal space in humans. There's a lot of interest in neuroscience around this concept. This is something that I looked at during my PhD. But this concept basically says that in this region of 20 to 40 centimeters around the robot's body, humans integrate information from vision, from touch, from auditory signals. And we do that because this area is particularly important for our safety. So we can extrapolate this principle and translate this to robotics, but we can also look at superhuman capabilities when doing so. And in particular, we can say, okay, what about rather than just detecting touch, detecting the contact, what about we start perceiving objects through proximity sensors that are distributed along the robot body? And this information is something that doesn't come easy to humans. We do some sort of sensing at a distance through our body hair, but not too much. But this capability allows us to cover the spectrum between perception at arm's length and perception on the robot's body. So what you're doing with this is basically to bridge the you're bridging the perceptual gap between vision and touch. So on one end you have a very well explored area, which is distal sensing through vision. Vision gives you a lot of useful information. It's information-rich data, but vision again is suffering from occlusions, it's low bandwidth, and so on and so forth. On the other hand, you have touch. Touch is great because it gives information about collisions. It gives information that is relevant at all times. However, at times you don't want to wait for a collision to happen before reacting. At times you want to predict what happens in this liminal space in between far sensing and on-body sensing, and this is where proximity sensing can be useful. Okay, so one hypothesis that we're investigating in our trend is the hypothesis that by achieving dense and rich perception in this space, we are going to be unlocking new capabilities. So to investigate this hypothesis, Mary set forth to develop a set of hardware designs that you have multiple designs, but they all have one thing in common, which is the fact that they can sense proximity, can sense objects in the proximity of the sensor by means of a time of flight sensor, just an infrared. You send an infrared signal out and you wait for it to come back, and you can use that to retrieve the distance of objects with the sensor. These boards are self-powered, they are self-contained, there's a Wi-Fi chip, so you can basically take them, power them with a phone battery, stick them onto the robot, and perceive objects in the proximity of the robot. Together with a kinematic calibration system that basically allows to locate these boards on the robot's body, then we can retrieve the 3D pose of objects in the environment. And thanks to these boards, we can also approach another problem, which is the problem of sorry, let me remove this because it's line. Okay, back. Okay, which is the problem of the problem that I mentioned earlier, which is the fact that collisions are inevitable. The environment is too constrained, humans are faster. Traditional controllers in these spaces would just catastrophically fail. If there are too many constraints, the robot stops operating, and that's not acceptable in realistic scenarios. But by having this rich perception in the proximity of the robot, we can move away from this paradigm of avoiding obstacles at all times, and we can move toward the paradigm of allowing for contacts as long as they are safe. So Caleb and Matt worked on a framework that allowed to demonstrate this capability. It's composed of 4 steps. The first one is perception in the nearby space through these sensors. The second one is obstacle avoidance. This is just to get up to speed with the state of the art. And more interesting, if an obstacle avoids avoidance. So this is something that will break the controller. The controller that Caleb has developed would accommodate collisions where inevitable, would make the robot more sensible to force interactions, would slow down the robot, and this would make collisions safer. And by having safer collisions, then we can be a little bit more aggressive and a little bit faster in recovering our trajectory and handling the contact. So again, the first step is our perception. We are perceiving only through proximity sensors. Obviously, in the idea case now, the hypothesis that we also start with this very low level data. And importantly, proximity sensing is much faster than vision, 3 times faster than a traditional camera sensor. And this is what we argue is enough in this safety focus. Looking more. So
if you click on the chat and just look at it, then afterwards it'll hide the whole bar.
Ah, really?
Okay, nice chat.
Glad
Okay, yeah.
You know, after 2 years of this. Maybe 3 years, I don't know anymore. Okay, cool.
But now it's spinning, sorry.
Now it's spinning. Okay. You can't have everything, you know. Let me find my mouse in this other screen. Okay. Let's try again. Okay, so we were. Oops. We are here, and I was going to transition to step 2, which is obstacle avoidance control. When an object enters this region of interest around the robot's body, then I can create a robot controller that uses this information to stay as far away as possible from the obstacle, while at the same time satisfying the main task trajectory. And this is done in a velocity control mode, which means that at every 10 milliseconds, we are sending a velocity to each of the 7 motors of the robot. And this is done by exploiting the redundancies that are intrinsic to the kinematics and the mechanics of the robot. This means that not only we are able to avoid obstacles, but we are also able to stay as close as possible to the main task trajectory. This is done in a quadratic programming formulation. There are a lot of equations in between these two things that I'm not going to be covering. But another addition, another capability that perception in this space allows is that when an object comes in, I can slow down my end effector. I can still perform my task, just slowing down the end effector to be a little bit more safe and a little bit better at accommodating for contact. The other element of this equation is also restricting movements on the parts of the robot's body that are closest to the obstacle. So I can tell to this motor to not move in the direction of the obstacle, to only move in this direction. And I can tell with all the other motors to accommodate for this change in the task while we're controlling the robot. Again, there are tons of equations here that I'm going to be glossing over, but videos are better than equations. And this is just a quick demonstration of the integration of proximity reuse with this controller. These are just 5 skin patches that are detecting proximity data in real time. Right now, they're very far from the robot because it's like the ceiling, the floor, the walls. When the cable comes in, you're going to see this one getting closer to the robot. And when it overcomes a specific threshold, the robot is going to start to wait. And this is what happens over here. Obviously, Kane here being particularly annoying, just to demonstrate this capability, but also with multiple sensor activations. In this case, you just take the average reading from all these multiple sensors. But this is already a good step toward achieving better behaviors when working closely with people. But as I mentioned, the interesting thing happens afterwards. If I have an object that moves so fast, so much faster than me, and I cannot avoid it, I want to gently accommodate for contact. And I do that by, oh, there's no way. This thing, no. I do that by, I'm gonna be talking about it because otherwise we're never gonna end. I do that by computing, okay. Let's start the program. Number 2, sorry for that. Obviously, I prepared this and it didn't work, it didn't happen. Okay. Okay, almost there. Okay. I do that by detecting collisions with a dynamic force threshold that depends on a number of parameters, the estimated external force, flow dynamics, and a number of other things. But most importantly, that varies depending on the presence of an object and how far an object is from the robot's body. And this, as I mentioned, that allows for the robot to be more receptive and be more aware of whatever happens in surroundings. And by doing so, we can also achieve better post-contact behavior. We can recover the main trajectory faster, and so on and so forth. The only graph that I would like to show you today about this is this one, in which we show that with proximity, we are having conditions that are more or less half than the induction force you would have without this prior to contact behavior. Okay, so sorry, video is nice. I hope it's not going to freeze my computer. But what you can see here is the same behavior as before, but this blue line here is just showing the force threshold that we're talking about. When Caleb comes into the proximity space of the robot, these forces become lower, so that the robot is more receptive, and the collision is detected before you will be able to do. You will be able to detect it without such a system. In conclusions, this is a good example of what I mean with having a systems approach to robotics, because we looked at how a new perceptual capability unlocks the robotics capabilities downstream. And again, this is something that people have been investigating, but people have usually stopped here, avoiding contact when you can, and then stopping the controller when you can't. But what you can do with this new perceptual capability is also accommodating for contact, reducing the contact force when inevitable, and being able to resume your trajectory faster than the state of the art. Obviously, this is a very first step, but I think that this is also a very important step that allows us as a community to shift from avoidance at all costs to prior to contact behavior. Caleb and Natalia are also working on a number of follow-up works. This is an iOS 22 paper that is basically a benchmark to validate multiple controllers in physical human interaction. And there are a lot of other little things that I'm going to be showing you later. But this is just a good summary of the type of research we do in strand 1. Let's move on to strand 2, which is focused on the robotics proper. And it looks at improving the state of the art for robots to operate in these complex environments. Again, human-populated environments are very hard. And one of the things that will prevent a robot to have business sense in this application is the fact that, as I mentioned, humans are much better than robots at manipulation. We are better because we have better hardware. The human hand is one of the most complex components of our body and part of our evolutionary advantage. But we are also better at interacting with the environment in a variety of different ways, including to use. We not only grasp objects, but we can also interface with the environment in many other different ways. And this is in stark contrast with the state of the art of robotics that typically focuses on research that advances grasping manipulation, which is pick and place, moving objects from point A to point B, and so on and so forth. However, both humans and animals, there's a lot of interesting stuff on crows, are able to interact with the environment with in a lot of other ways. You can throw, kick, toss, flip, pull, push objects, and this is coming at an evolutionary advantage when you are operating in these complex scenarios. And importantly, this is also a fairly underexplored area of research due to the complexities of the interaction between the agent and the environment. There is a completely different need for state sensing in this space, and also you need the different and better dynamical controllers to operate in this space. But if we were to deploy robots in these complex scenarios, this could be one of the many skills that a robot could use to operate a manipulated environment. So Anush, together with Ishan, set forth to investigate the hypothesis that non-prehensile manipulation, which is anything but grasping, non-prehensile manipulation is important and useful for robotics, and among all these possible non-prehensile manipulation primitives, that poking is the most fundamental on one side, and also the most complementary to grasping. Because if you look at grasping, again, we have a lot of research in manipulation prehensile manipulation, but grasping is limited by the physical capabilities of the robot, is limited by the robot. So each is limited by the gripper. If you have too small of a gripper, you cannot grasp, right? So you have to design your environment around the limitations of the robot. The most explored non-prehensile manipulation primitive is typically pushing, but also pushing is limited by things like robots. So each the manipulation speed, you have to slowly push objects around in order to succeed in your task. On the other hand, poking involves impulsive manipulation, and it doesn't have these limitations. It can operate outside of the boundaries and outside of the reach of the robot. It can allow for faster manipulation than pushing, and it doesn't impose strong restrictions on the properties of the object. So all of this makes poking very interesting for robotics. And to investigate this hypothesis, we started by formalizing a control primitive for poking. This is pretty straightforward. You have an object in a planar surface, you identify a target control point, and then you send a control command to your effector to push this object with a specific velocity, which basically sets the object in free sliding motion until it stops the friction. We base ourselves on this formalization of the poking primitive, and then we created an RT-based algorithm that combines this control method with a traditional sampling-based motion planning. I won't go through the details of this, but the most important component with this approach is that it's action-oriented. All the nodes in our graph are valid configurations, and they are valid configurations because we are integrating this approach together with simulation in the loop. Modeling the mechanics of friction is still very hard to do and state-of-the-art in mechanics. And by using a simulator, we can basically short-circuit this need, because the robot can simulate a lot of different pokes in simulation, and we can use that as an information for our motion planning. We evaluated poking against these are the two primitives, pushing and grasping. Again, here we are not looking at poking as the solution to our problems. It's more about poking as a good complementary capability to grasping. We have a variety of different scenarios, and we are motivated by this true robot collaborative style in which a robot needs to pass an object to another robot. So for the three easy scenarios, we have multiple objects in these scenarios, so these become gradually more complex. But for these three easy scenarios, all these capabilities are perfectly capable of performing the task. Grasping is a little bit better because grasping can just go over all these obstacles and complete the task. But when we start looking at more complex environments, in this case, you have an object that is too big to be grasped, but then we can start seeing how poking can be useful, because again, grasping is going to be failing in this scenario because it doesn't, it's not allowed, cannot pick this object, right? Poking and pushing can still complete the task. Poking is like better. Scenario number 5 is a scenario with an overhead obstacle. You have a tunnel over here. In this case, grasping can succeed, but pushing can fail because it cannot push underneath the obstacle. Poking, because of this impulsive interaction, can still succeed in the task. And lastly, you have a scenario in which the operational spaces of the robots are not overlapping, so they cannot pass enough to each other. In this case, both pushing and grasping are going to be failing because poking can impart high impulses on this object. You can still poke it across various boundaries. All of this is very qualitative, but all of this is supported by simulation and a lot of numbers and the tables. That's what we do in motion planning. These results reflect the qualitative observations. Poking is faster than pushing, which makes it better than pushing, and poking is also more generally applicable to all these corner cases that I just showed here. In the real world, similar things with the caveat that simulating friction, as I mentioned, is very hard, which means that you're going to have higher task times when performing these activities, these actions. Poking allows for planning on the fly, which is also very important. If you fail at grasping, you have to start over. If you have a poke that doesn't push the object exactly where you like it to be pushed, then you can replan on the fly, and you can take that into account. What I think is particularly interesting, beyond demonstrating that poking is useful for robotics, is also the fact that as humans do, we interact with the environment in a variety of different ways. So one of the things that Anush is working on in terms of future work is creating a planner that is able to plan across these different capabilities. So again, grasping is great and it works 80% of the times, but what if we're giving it a plus 20%, plus 15% when we add poking and we effectively plan across these complex manifolds that the robot can take advantage of. So this concludes the second strand. Again, we're doing a lot of other things in here, but I'm going to be moving to the third strand, which is the one working in algorithmic and social human interaction. This, as I mentioned, is the strand that focuses on the robots being better teammates. After robots that are safe, robots that are better, then I can start thinking about, okay, maybe I can deploy these robots in my application. But there's another final element of this equation, which is the fact that humans are great in these scenarios, also because they are great at working together. And again, robots are pretty bad at that, okay? It's hard to perceive humans, it's hard to understand what they're doing, it's hard to negotiate and synchronize between the human and the robot, and it's also hard for humans to understand and predict what the robots are doing. So what I'm going to be showing today is a work from Claire and Maria from Red's Lab that investigated these last components of predictability of robots' behavior, and they did so by looking at yet another human capability, which is the fact that humans are primed for patterns. This is a natural reward system for robotics. This comes from, again, our thousands and thousands of years of evolution. It simplifies our perception. It's important for us to have fast reactions to perceptual events. And this means that we are reacting better to threats in our environments and so on and so forth. In general, pattern recognition has been honed by millions of years of evolution. Everybody that doesn't have a cognitive disability is able to recognize a face in this tree, a guitar in here, or the triangle in this optical illusion. And these are examples of perceptual patterns, right? But the same can be said of behavioral patterns, which is behaviors that follow a specific set of rules or constraints so that they are better predictable by an agent. So the research question that Claire and Maria are asking is, can a robot that expresses pattern-like behaviors make for better robot teammates? Okay. And we do that by playing a game with the robot. In this case, games are great. In this game, you have a board with a number of objects, different shapes and colors and different positioning. The human and the robot need to pick an object from the board. They don't know what the other agent is doing. If they select the same object by color and shape, they get a reward. You remove the object from the board and you continue. If you don't, you fail to coordinate, you get a penalty and you have to try again. What we really like about this game is that there are hundreds of possible patterns for each of these boards. You can have behavioral patterns, so you can choose to select objects based on color, shape, positions. This is just some examples of them. Some of them are better than others. For example, the first one is very vague. Picking all the yellow blocks plus then the blue blocks and then the red blocks makes it very hard for a person to synchronize them. The last two are a little bit more specific and allow the human to better understand what the robot is doing. So there are multiple patterns, and what we want to do is to rank them and to score them against a metric. And the metric that Claire developed is an entropy-based metric. And the goal is to identify the least ambiguous pattern given a specific board game. Okay, not given a specific board game. This is basically composed of two components. The first one is the entropy of all possible patterns that have matched thus far, which means that you're going to be preferring a pattern that is unique. And the second one is that if you have fixed your pattern, then you're going to be choosing one with the most unique set of actions. Okay, this all of this to say that you're going to be favoring patterns that are unique and patterns that become unique as soon as possible. Again, we have created a number of possible games and boards, 30,000 boards and 300 patterns per each of these boards. And we have created an experiment that validates our assumptions against three conditions. The first one is a reward maximizing policy. If the human and the robot were to perfectly synchronize, this will achieve the highest possible score. This is normalized up to 100. So if you are perfect and working together, if you are an F1 team, this is what you will be doing. F1 team, apart from Ferrari this year. And this is compared against the best behavioral pattern according to our entropy measure. This ideally doesn't get to the same level of performance of this one. However, if this allows for better synchronization, we would be much closer to this theoretical number because we would synchronize much quicker. This is also compared against the median pattern, so the pattern with the median entropy, which in this case is slightly better than the best pattern in theory, but not in practice. We ran 27 participants, now 9 per condition. This is an in-between subject design. Each participant is doing 3 rounds, and each participant is exposed to only one condition. And these are scores that they achieved during this game. You can see here the ideal case scenario for the reward maximizing robot is 100, but the average across 3 rounds gets to 18. For what concerns the best pattern, the theoretical best score would be 83, but what we achieved is 79. So other important metrics, the teams were doing fewer mistakes. So all of this is very nice, statistically significant, and so on and so forth. But most importantly, we don't want to necessarily look at this as a game or for the perspectives of the specific implementations. What is very interesting for us is the fact that the perception of the robots by the human participants were much improved when the person was playing with the robot and was following a pattern. So here again, there are a lot of interesting measures, but in general, people preferred playing with the robot that was having patterns. People thought that they wouldn't have scored better if the teammate was human. The robot was more predictable, the robot was more understandable, and so on and so forth. So to conclude, yes, this suggests that behavioral patterns are useful and important in improving the coordination between human robot teams. But what I think is more interesting is that this is just an observational study, right? So we can observe this behavior, and it's interesting behavior. What I think is very interesting is how to use this little trick to our advantage in future work. And again, there are plenty of examples. Together with Brad, we have a couple of, actually with Brad, we have only one project with from the Army Research Laboratory. We are exploring the consequences of this finding, and in particular the fact that, for example, you can use this for aligning behavior when you have changes to the face of uncertainty. So you have a perfect team, they work together, something happens in the environment. How can we synchronize again to operate in this new environment? We can use these little tricks to make the team work better and faster. But we can also use this for human-in-the-loop decision making, for policy learning. If you have environments that are suboptimal by design, there's no notion of optimality, but maybe thousands of possible suboptimal policies. You can use this information to discern which behavior would be better in the context of teamwork. Okay, and again, there are a lot of other interesting directions that I think that this work can lead towards. Okay, so this ends. I have no idea what time is it. It's a little bit late. But this ends the third part of this presentation. Let me move to summary future works really quick. As I mentioned, this is what we do. We want to work towards these objectives, and we want to do that by looking at what is the systems and by contributing back to the state of the art. I think it is important to focus on these three domains individually, but also to look at the intersection of these fields. And in terms of future work, I think and I hope that our research is gonna go in two directions. On one hand, I would say I would call it expansion, expanding research in these areas, and on the other hand, I would like to consolidate research across these areas. So, don't want to spend too much time on this. We have a lot of interesting things happening for each of these trends. Natalia is her GFRP is on motion planning for in touch. We have a lot of other papers. We are working on new hardware. We are starting a project together with Carson Burns from Atlas and Dan Safier on deploying these robots in organic chemistry laboratories. These are as dangerous as a professional kitchen. There are a lot of people that die in these scenarios. So this is a great validation of all the things I was talking about. And I'm very excited about this. This just started last week. So we don't have any result. For what concerns Turn 2, as I mentioned, we are looking at multimodal planning across skills. Gilberto and his fellowship is translating this idea to the problem of failure recovery for space exploration. So if you have a robot in space that is manipulating the environment and you have a failure that you didn't plan for, you didn't expect, you can use these multiple skills to still perform the task, at least part of the task, with the rest of your body. And in my opinion, this is a very interesting direction. Joey, together with Rohui, which was a PhD student of Dijon, worked on multi-agent reinforcement learning and multi-objective reinforcement learning. And finally, Stefan worked on intersecting robotics and with natural language. So models that can reason about physical events and using this information to improve our understanding of language. Lastly, step 3, we have tons of projects that started this year. On top of the things that I just mentioned, we have a project for the UNR on task allocation and role assignments, so how to synchronize quickly with humans. We are having an important effort for what concerns the NSF Institute in Student AI Cleaning, and this is basically in two directions: human-in-the-loop reinforcement learning, which is Joey. Joey is the reinforcement learning person in my lab. If you're interested in that, reach out to him. And also robots for education, which Caleb is pushing forward. There is a robot over here. Oops, sorry for pointing it later. There is a robot over here because she's running a study and she needs participants. So if you are interested in these type of things, please reach out, because we need people to do these studies. And this again is what I meant with expansion. So there are a lot of stuff that is happening within strands. But what I think is very exciting to me is consolidation, which is research that happens at the intersection of these projects and also across different strands. So this is just a little game that we did over the summer with my students, in which we were just looking at, oh, if we were to work and collaborate with somebody else, who would that be and why should they do that? And again, we are not going to be covering all of these collaborations in the future, but I hope that we're going to see more of these things happening in the next few years. Do not hold me accountable because this doesn't depend on me. I'm just trying to convince my students about this. But with that said, I'm going to end here. Thank you again. Thanks to my students, first of all. Thanks to my graceful funders that made this happen. And lastly, thanks to all the collaborators, students that passed my lab. I couldn't put all the pictures. I probably forgot somebody. And in particular, thanks to these 3 guys right here, with which I shared the countless discussions, papers, projects, proposals, peers, and also a book that we are publishing with MIT Press, Introductory Robotics book, by the end of the year, I think. So thank you all, and I'll be happy to take any questions. Questions? Be shy. Nice picture, right?
Yeah, very nice. So you mentioned, I believe it was in the book RT discussion, you're saying that you're using, that was the one where you're using simulator?
Yeah.
Simulator, but physical, like Christian models are included into the simulator and are not great.
Then very bad.
Yeah.
And that's yes.
So I'm curious, is it the amount of sampling that you do that helps overcome the limitations of the simulator? You sort of get an aggregate of what the likely outcome would be, and maybe you put a finer point on it. Why aren't you just using deep learning?
Yeah, no, these are important components. We try to use deep learning. We didn't go very far, but that's one of the directions that we try, especially because, as you mentioned, simulators are pretty bad at that. So what would be really interesting is to have a true mechanical model of friction, which again is state of the art and not my research. So we have explored the direction of doing of using deep learning based approaches to that, and this is definitely interesting. We haven't gone very far so far, but that's definitely something that we are exploring. Yeah.
Do you have any classification of risk around the code? For example, people get outside the robot workspace and the friction is a different model and now something no robot can reach it? Is there any kind of like accounting for that in the planner?
Yes, that's a good question. So we implicitly do that through the simulation because you are simulating all these boxes in different configurations. So you are implicitly doing that. But I think that having a strong quantification and understanding of the limits of each of these skills, depending on the state space, is one of the things that that make all of this interesting. Because again, this is something we are discussing a lot with Anush and Gilberto. Because again, you have this state space, you have multiple manifolds. You're asking, putting, pushing. You would like to really characterize where one is better than the other, right? And that's basically the direction we're going with this multimodal motion planning.
So regarding this, okay, so modeling the mechanical, the dynamic of the object, while you folks, I think that's a hybrid dynamic, right? Because the moment you put the impact, so there will be some dissipation or something.
Yeah.
So is it possible to like come up with a simplified model which approximates the reachable states of the object when you pick? So now you have an over approximation.
Yeah.
But then that's also good because sometimes you want to reach the target, but sometimes you want to also avoid going to some region, right? So if you come up with that over and under approximation using a simplified model, then that helps you to at least with like 100% guarantee say that, okay, I know for sure I do not go to the bad region, right? And maybe that's one way of going to using the simplified dynamic in that case. I think that's it.
I think this is directly correlated to what you said, because what we are seeing is that we can have very good predictions in simulations, but when you deploy them in the real world, it breaks, right? And so what we are trying to do when quantifying the limits of each of these skills is doing, for what we also spoken, is exactly doing that. Rather than saying, I want to go there, and if I do this control command from this point to the next, I'm gonna get there, you can start having some noise around your estimation, right? And this should be, your variance or whatever, right? You can start having some noise around your estimation, and this is something you should also take into account when planning for it, right? So you can have also obstacles around it. These obstacles are constraining your environment in such a way that your noise gets directed in a specific direction and so on and so forth. But these two questions are exactly what I should be working on rather than me here. Yeah.
I guess related to this, so I'm interested of this problem. So as you perturb things that are perhaps hard to measure or hard to control, like there's a grain of sand on the table or there's a smear of food or whatever, that may significantly change the trajectory.
Yeah.
And the other techniques perhaps don't suffer from that ill conditioning or very high variance.
Yeah.
Was that a thing that you?
Yeah, no, definitely. And that's again, I wanted to say a lot of things. That's why I didn't spend too much energy in all the details. But what working is needs is also for it needs a lot of planning, because all these little things and all these simulation errors and all these other things, they basically result in a poke that doesn't go where you want it to, right? But the advantage of poking is that you can still get close enough and just do a little planning to still achieve your task. Whereas if you have noise in your perception system and you just fail at grasping because you think the object is here, but your perception system says that it's here, you can't do it. You're just failing, right? So we also take, this is something that we haven't explored yet, but we also consider that this is one interesting space in which we should be planning for. Yeah.
You mentioned the robotics scan. I was wondering
Yeah.
how was that data for how we're using that?
Yeah. So robotic skin, let me go back. So right now, again, we are just doing a lot of little prototypes. These are the first 2 prototypes. Mary is an exceptional electrical engineer. I don't know anything about it. Only thing I tell her is that, oh, it would be really nice to have all these things on the board, and she makes it happen. But basically, the way which we works is that we buy off-the-shelf sensors, all this stuff, that you can buy from all these electronics places, and you have, you know, that's about $1 each or something like that, and then you can send all of this. You can fabricate it yourself, or you can send it to companies that do that for you. Just the parts is around $25 for this type of things if you do it yourself, and if you go to a company, it gets to something like 40-ish. So still a low cost, but again, these are just a lot of prototypes. We are working also in another set of prototypes. Where is it? Here, you know, soft hardware, color changing schemes. And again, all these are interesting things. I would really like to have hundreds of these sensors at some point when we finalize a design that we decide this is it. Rather than trying with 10, we're gonna try with 1,000, but we are not there yet.
Alessandro, we have a question.
Okay.
Danny, do you want to unmute or do you want to ask a question that you?
I can unmute. Let's see if can you hear me okay?
Yeah.
Okay, yeah, Alessandro, thanks so much. It was a very nice presentation. So I think in one of your slides, maybe even the one that you're showing right now, you were talking about an upcoming deployment in some chemical engineering. Maybe it was this slide or another one. Can you tell us a little bit more about what excites you and who's the partner and what excites you about some real world deployments of this cool research that you're doing?
Yeah, so this is a collaboration with Carson, who is in Atlas, and he's a mechanical engineer. Atlas is mechanical engineering. He's an organic chemist, and he does a lot of cool stuff like programmable tattoos and stuff like that. We basically sit together and we started to think about the fact that it would be really nice to have robots in these spaces because they are very dangerous and super stressful. And again, there are significant safety hazards that result in, literally people dying every year in these spaces. And so we found that this is a very strong justification for exploring this space with robotics. But on the other hand, it's also a nice segue from what I just shown in this specific strand, which is I want to have robots that are safe, I want to have robots that perform in these challenging environments and so on and so forth. So what is really exciting to me is that this could be the first demonstration of all the things I said in a realistic application. Does it make sense, Danny?
Yes, thank you.
Nice.
Yeah, if you can save people from dying from poisoning, I guess, or there's a lot of chemicals and gases that get so yeah, that's a good thing of keeping more people alive. Good job.
I think we have maybe time for one more.
Claire.
It was about that optimal strategy that has score 100.
Yeah.
You just cannot bound the entropy in a non-trivial way, or did not list an entropy on that.
Let me pull it up. That's a great question to ask. Wait, Claire.
Oh, Yeah, so the.
Sorry, let me say it again. The question is, why don't you have an entropy rating in there when maximizing policy? And I
So-
think I know the answer, but I think she knows better.
Yeah, so the sequence developed by the reward maximizing policy is not developed by the equation. It's essentially if, assuming perfect coordination, what is the sequence of blocks that will result in the highest possible score? Which looking at it is just not feasible, but in theory, if we let the robot sort of decide on its own to maximize the reward, that's what we're
I would say that you can compute the entropy score for this condition, but it would be very tied to the specifics of the game, so not necessarily interesting. But yeah, I mean, this is a good point. I probably should have placed the number on that.
Let's thank Alessandro again.
No, stop sharing.
So it's not.